Oh, cool. All right, is this thing on? We're working? How are we doing, folks? I know, thumbs up from me too. I'm stoked. This is looking to be a cool conference. I'm feeling very, very happy to be on the stage here, getting to share some neat stuff with you. All right, so today we're talking about hardware insecurity or hardware security, because every device needs hardware security, all right? Your smart cards, the credit cards in your wallet, the key fobs you use to drive your automobiles, they're not internet connected, but that doesn't matter. Because if those were to fall into the wrong hands, we want to make sure that someone who opens them up, who starts probing, can't cause them to do things we don't want them to do. All right, so here's kind of the spectrum of attacks we're going to look at, starting with things an attacker might do that are very easy, very inexpensive, very simple, all the way to attacks that are much more complex or expensive or difficult. All right, so a little bit about me. In 2010, I graduated from Harvey Mudd College. I spent 15 years doing cool stuff in the military, among which was getting to teach at West Point. The military sent me to NC State to get my master's degree in computer engineering. I'm out now, left in June. You can see a picture of my beautiful family there, wife on the right, 2 kiddos. And we live in Tennessee now, and I'm doing writing some technical content for DigiKey. So that's what I'm up to. Got to present at a couple of different conferences and blog for embedded related. So it's been a cool couple of years. All right, I'm trying something new today. I'm an educator at heart. I want to make this fun. So I've got prizes. Okay, we're gonna do a Kahoot and at select points throughout the presentation, and there's a chance to win. Firstly, a chip Whisperer Nano. All right, so you'll see me demonstrate this today. This is a little piece of hardware made by Colin O'Flynn over at New AE Tech. It's a little development board that combines a SAM4S microcontroller that you can control from their Python library to conduct hardware attacks. And then on the end is a little STM32 microcontroller that comes bundled with it. So right out of the box, you can start conducting side channel or fault injection attacks. And then second and third places are, I've got copies of the Hardware Hacking Handbook 4. So this is a great resource to kind of get more in depth into the attacks that we'll look at today. All right, so the first thing an attacker might do if they've got access to your device is just see what information they can gather, all right? Product manuals, repair tutorials are clearly pieces of information that they might glean, all right, try to use to gather information about a device. But with a little bit of digging, they might be able to go even deeper, right? They might be able to find the GitHub repo for, that device if it wasn't set to private. They might be able to find someone else's reverse engineered schematics. If there's a patent ID or an FCC ID on the device, well, then they can go to those respective offices to try to find those filings, which is going to include information about the device that, why it meets FCC requirements or why it's warranted a patent. And all these things, individually might not necessarily seem like they expose a ton of vulnerabilities in the device, but they absolutely can, and they definitely can in aggregate. In 2018, security researchers used patent filings specifically to expose backdoors in the security mechanism of x86 CPUs, and in 2020, security researchers used information they found in patent filings to defeat the Cisco root of trust. So the information that's potentially available absolutely enables or can enable hardware attacks. Attackers can get even more information once the device is opened up. Okay, so if we haven't intentionally tried to obfuscate anything, then they can read off the part numbers of each of the integrated circuits that are on the board, so they can find the exact model of the microcontroller or the CPU we're using. They can know exactly which flash we're using. If they work hard enough, they can reverse engineer the schematic from just probing around the PCB. They might even find some unlabeled ports. Maybe these were ports used in production to flash a secret key onto the device that, of course, is not going to be populated for the user. But if a hardware attacker can find those pins, then they've got access to a port potentially that goes into the device. And as an attacker, they're going to be kind of looking for these things. All right, so once an attacker's done an initial round of research, they might continue their probing around the circuit board, specifically looking for those ports, those JTAG or programming ports that were used to flash the device, any sort of serial communications like UART or SPI or I2C, even if it's just going to a sensor and back. And with these things, they might ask, well, did the manufacturer leave the JTAG port unlocked? Oh, that's a huge vulnerability, because at that point I would just need to attach a debugger to get full access to the device. But even if it is locked, like we'll see later, that locking protection, that mechanism, might be vulnerable to a fault injection attack. We might be able to get the chip to sort of glitch a bit and give us access to the device. All right. Maybe we encrypted our firmware when the user was doing over-the-air updates, but if we weren't careful, if an unencrypted version of that is loaded into the microcontroller on startup from an external flash, well, then all an attacker needs to do to read the unencrypted firmware is just probe that memory bus. Maybe we just look at signals that are going from the microcontroller to other sensors or peripherals on the printed circuit board. That might not necessarily lead to a vulnerability, but we could get the microcontroller to think erroneous information, right? If it's attached to a temperature sensor, I could potentially tell the microcontroller, give a faulty sensor signal to say, hey, it's 1,000 degrees Fahrenheit, or it's -1,000,000. And that might inadvertently cause a buffer overflow or something, or an integer overflow later on. In fact, the PlayStation 3 hypervisor was actually hacked in 2010 using this exact method. Attackers glitched a little logic line between the microcontroller, or the CPU and the memory bus during a free operation that caused an actual memory leak in software. And then attackers were able to exploit that memory leak to gain control of the whole device. And it all started with just putting a little probe on that signal line between the CPU and the external memory and glitching it at just the right time. Additionally, we can get information as attackers just from the timing of things going back and forth. We'll see later that if I can measure how long it takes a device to perform certain operations, that can leak enough information to allow an attacker access to a device. Lastly, the attacker might actually start modifying this PCB. So I've already kind of mentioned how I might just not be probing around. Maybe I'm actually sort of disconnecting certain traces and injecting my own signals. Lots of SoCs and CPUs come with external pins that control the boot configuration. So I can start soldering or desoldering strap resistors or pull-up or pull-down resistors to change the configuration of the device potentially, to cause it to think it's booting from a different piece of hardware than it was configured for, or something like that, to cause an attack. If there's a piece of external memory on that printed circuit board, then I might be able to lift that off to desolder that and then read out the contents. And if it wasn't protected correctly, rewrite my own contents to that device, solder it back onto the board, and now my device is booting from memory that I just wrote. All right, so take a second, introduce yourself to the person sitting next to you if you haven't already, and get your creative wheels spinning. Ask them what other attacks do they think might be enabled by an individual who just had access to a device. I've got a question up here. Yeah, no, I got an attack. Oh, you got an attack. Okay, tell it to, there's a fellow sitting behind you. Tell that to him. We'll go again in a minute. All right. So critical point for me from just thinking about this is that there's lots of hardware attacks that really are not difficult to conduct. And a point I'll hopefully kind of belabor over the presentation is that your device, even if it's not internet connected, should have a threat model. You should be thinking about how individuals may attack your device, including just sort of probing around. And you will hopefully, as you're developing things, are conducting that security analysis. What are we trying to protect? What are we protecting against? And what sorts of countermeasures do we feel like we need to have in place to prevent easy attacks? Okay, Kahoot. Woo! All right, so here we go. Hopefully I think I've got a legacy account, so hopefully this doesn't kick us out after 10 people. All right, here's your game pin. Go ahead and pull out your phone. You can navigate to kahoot.it or scan the QR code to put in that pin. And then I got a couple questions for you. No! No! Okay. All right. We'll still show the questions. I'll figure out another way then to make this fair to parcel those out. So if you were not able to join, then you can just sort of think through your answer when we start this. All right. All right, first question, true or false? With regards to onboard PCB signals, attackers are only concerned with the ones carrying cryptographic information. All right, excellent. False! Yeah, I can do lots of fun stuff with not just necessarily cryptographic things. All right, number two. Which of the following is not a useful piece of information that an attacker could get by reading the data sheet for the CPU? All right. Yeah, IC package size. I think all the other ones of these, right? What are the functions of the pins around the CPU? What are they doing? Are they memory buses? Are they GPIO? Are they different power nets? These are all important things. Operating voltages is important to know, not just how we're operating the device, but what's out of my operating voltage range. How could I start to kind of get this device to do things that it wasn't intended to do? Definitely boot configurations. Okay, excellent. Back here. Okay, so the first, I don't want to say real attack, but the first place where we get this gets really interesting are side channel attacks, all right? A side channel is a way that a device leaks information about what it's doing through just the byproducts of its operating, all right? So in the same way that like detective work, like it's founded on the idea that criminals leave behind clues to what they did, even if they were trying to cover their tracks. Microcontrollers and electronic devices will do things in the course of even cryptographically secure operations that leak information about what's going on. So these can include the electromagnetic radiation from the device. The two big ones we'll look at today are the power consumption of that device or how long it takes to execute things, but there's a number of side channels that we can all attack to try to figure out what's going on in this device. All right, so every device is going to leak information about its operations and its data. We'll talk towards the end about countermeasures. That the best we can do as developers is to try to sort of prevent someone from gaining enough information from what our device is leaking to do anything useful. All right, so I can use execution time to figure out what a device is doing. Here's a very simple example. A website might tell me an error occurred if I logged in, but if there's a difference in time between when that message comes back to me, I might be able to sort of consistently figure out when I've entered my username correctly. If the server takes just a little bit longer when the username is correct before it checks the password. All right, here's an example using like a password login. So maybe my device has like a little, a UART shell that is hidden in the PCB for developer access. And if I connect to it, I see this little prompt that says enter password. A really typical configuration on the device side might be, hey, we're going to ask this person to enter a password and then use string compare. We're going to compare that byte for byte to what the actual password is. If it's valid, we'll grant them access. Otherwise, we kick them out. This code is susceptible to a timing attack exactly because string compare is going to go byte for byte and return as soon as it knows the two strings don't match. So if we send our device a string of incorrect passwords and one of them takes just a little bit longer than the rest to come back with that access denied message, we've found the first correct character in that password sequence. And so instead of having to brute force over 1 billion passwords, assuming this thing has a 6-digit alphanumeric passcode, on average, we only need to test 108. Because within about 18 guesses, right, I can get that first character, and then I just have to do that 6 times. And this is not a made-up scenario. As recently as the mid-2000s, you could buy a pin-protected hard drive. Yeah, this thing's not going to mount to your computer unless the user types in the correct pin. Super secure. But the software on this thing was vulnerable to a timing attack. All you needed to do was open up the case and probe the signal that went to the error LED. And you could type in a pin and watch that signal come back. And when you typed in the first correct digit on that pin, it took the hard drive just a little bit longer to light up the error LED. And very easily, you could use this timing attack to access the hard drive. All right, so take a second, look to the person next to you. How might you fix this code? We'll talk, I'll give you a couple suggestions at the end. But I think some of us are creative enough in this room to kind of start to hypothesize how might we fix this code to prevent a timing attack. So take a sec to see if you can come up with a solution with the person next to you. All right, like I said, we'll see some tips later potentially about how we might rewrite this code to close off a timing attack. Let's look now at power consumption. All right, so we're going to analyze what's going on inside a microcontroller or a CPU by just measuring how much power it's drawing from a supply. Okay, so it probably should come as no surprise, right? If we're measuring the power consumption, we can use that to tell really coarse things like the device is doing something really intensive right now, or the device is asleep, okay? But we can do better, all right? We can potentially differentiate between 2 operations the device is doing. So if there's a sensitive operation, there's a key point right in the middle of that operation when the device is either doing, we'll say, multiplication or addition. Assuming multiplication is a little bit more intensive for the microcontroller, we can tell the difference between those 2. All right? Now, you're not necessarily going to be able to do that just by looking at a single trace, because there's a lot going on in these things. So in order to figure this out, we're going to use some statistics. We're going to use something called difference of means. All right. So we'll start by assuming I can send a bunch of data to the device, and I know 100% that it's going to be doing multiplication. Okay. So I can collect a whole bunch of power traces of this device as it's doing multiplication. And then we'll say I can send a whole set of data to the device, and I know in that case that it's doing addition. So I can collect a whole bunch of power traces of this device as it's doing addition. If I take the groups of power traces for multiplication and average them together, I get a representative trace, where a whole bunch of noise has been sort of canceled out by the virtue of averaging all these traces together. And the same is true for addition. I'll get a representative trace of the processor as it's doing addition by averaging all those power traces together. If I subtract one from the other, for the most part, I'm going to get a graph that is all zeros, because this is the device essentially doing the exact same thing in both cases. So I'm going to subtract, I'm subtracting one from one. But there'll be a very specific point in this power trace when the device was doing multiplication in the top versus addition in the bottom. And there's enough of a difference in that power trace right at that moment that I can see a peak in this graph when I subtract the two. Now, it takes a lot of traces to do that, potentially thousands. In the cases of performing the attacks on real devices, you might need millions or billions of traces to really kind of to find this noise or this signal, but it's potentially there. Okay, so we're going to use this in a second to show. I'm going to show you how we can recover the AES key inside a device just by looking at its power. There's a couple more things we need to lay the foundation for before we get there. Number one of which, let's assume I didn't know whether the device was doing multiplication or addition in this little fake scenario. Let's say I just grabbed a power trace and I was trying to show what operation was happening. In this case, I don't necessarily have enough information to group these traces into multiplication and addition and define that signal. So I've got to make a guess, right? Well, let's say I make the guess that the device, when I send in an even number, it's going to perform multiplication, and when I send in an odd number, it's going to do addition. All right, so I can do the same analysis. I can group those traces by evens and odd numbers. I can take the average, I can subtract it, and I'll get one of two results. If, once I subtract these two average sets of traces, I get a little peak, that's my indicator that I've made the correct guess, that this is in fact how the microcontroller is separating the traces and what operation it's conducting in both cases. If I get a graph that's just nothing, it's mostly zero, what this is telling me is that effectively I've separated my two traces randomly into two groups, right? I've not made the correct guess as to what the microcontroller is doing internally, and so the result is just zero, okay? Even if I don't know what operation the microcontroller is doing, if I make a guess and sort and look at the result, that can tell me whether my guess was correct or not, all right? Power analysis can do more, though, than just differentiate between operations. I can detect if a single bit in this microcontroller at a point in its operation is a 1 or a 0. And we're going to use that fact to crack AES. So like I said, we're going to use I'm going to show you how to do what's called a differential power analysis attack. So I've got a device, we'll say it's doing AES 128 encryption in ECB mode. All right, I can send plain text data into the device. It does its encryption, but then I don't see the ciphertext. I don't know the key inside, but I'm going to tell you by looking at the power traces, we can figure out the 16-byte private key inside that device. All right, so to do that, here's a little background on AES. Forgive me if this is well aware. All right, so this is the AES encryption algorithm. At least in AES 128, the first step is to XOR the plain text with that 16-byte private key, byte for byte, right? Byte 0, the plain text gets XOR'd with byte 0, the key. Byte 1 and byte 1 and so on, all right? 9 times in a row, we conduct the operation subbytes, shift rows, and mix columns before we XOR the next round key and start the process over. On the last round, we just do subbytes and shift rows before we XOR one last time and emit our ciphertext. Importantly, the subbytes function is literally just a substitution. This is like an example here of what's called the S box, right? We're taking the output of this XOR, we are looking up a value in a table, and that's what we're emitting. All right, so I could write that very first couple of steps of the AES algorithm like this. Some byte of the plain text gets XOR'd with some byte of the key, and then I look up a value in my substitution box. So if let's say hypothetically, I knew that the output of the substitution box was a hex 1.8. If I knew that byte 0 of the input was hex 3.4, that would be enough mathematically, right, to figure out that the lowest byte of the key has got to be 0, 0, because I could just sort of work my way backwards from the S box to the XOR to what the key must be. In our DPA attack, we don't necessarily know exactly the output of the S box, but we're going to use just what we did here for difference of means and these power traces to make an intuitive guess as to what that key value must be. And that limits our sort of search space small enough that we can actually do this attack in software, all right? So step one of my differential power analysis attack is to conduct a whole lot of power traces of this device as it's doing encryption, all right? So what I've got here is a Jupyter notebook produced by New AE Tech to show how to use their devices to do cool hardware hacking stuff. This is one, this is set up now with my little Chip Whisper Nano here, which is doing AES encryption. And what I'm gonna have it do is just collect a whole bunch of traces, 2,500, all right? That's gonna go for a minute, and then we'll come back and take a look at the results. To conduct my AES, my DPA attack, sorry, on AES, I'm gonna make a guess at the first byte of the key. I'm gonna start with hex 0, 0, might as well, right? And since I know I can do an XOR, and I have the substitution box, I can, assuming the key is 0, 0, I can figure out what the output of that substitution box must be for each of the input values that I'm sending my microcontroller, all right? So here comes the part where I'm gonna do that difference of means to figure out if my guess was correct. I'm gonna take the lowest bit in this value. So the ones that are bolded here have a low byte of 0, 8 and E have a 0 in the lowest bit position. FF and D5, they have a 1 in the lowest bit position. So I'm gonna take the first and third sets of power traces, I'm gonna say, hey, right at the output of the S box, that lowest bit was a 0. So I'm gonna put those all in a group together, and I'm gonna take the second and fourth power traces and I'm gonna put them in a group by themselves, because the output of their S box and the lowest bit was a 1, all right? If I average those traces and subtract them, and that resulting graph there has a peak, then I have a confidence then that I've made the correct guess at key 0. Because if I hadn't, I would effectively have sorted my sets of traces completely randomly, and I would have gotten a result that was just nothing. There was nothing on the output. When I see a peak, that's my indicator that I've correctly guessed the 0th byte of the key. There's only 255 possible values. So in order to correctly guess the 0th byte of the key, I just need to make 256 guesses. And on average, after 128, I'm gonna find the right key value. Or I should say, I'm gonna do 256 anyways, whichever one has the biggest peak. That's my indicator that's the correct byte, or value of the 0th key byte. And then I just need to do that 16 times to recover the whole key. All right, so here I've got my traces. I'm gonna show you what a couple of them look like. There it is. There's the AES key. I'm kidding, this is garbage. I don't know what that says. Okay, I'm gonna go down here. Okay, and then this is the code right here that essentially says, hey, for each byte in the key, for each possible value of that key, sort my traces, calculate the difference of means, tell me what the peak value is. Now, critically, I'm gonna show you that for this firmware, I'm using the default key here. You'll notice it starts with hex 2B7E1516. All right, that's enough to show what's happening here. Now I'm gonna run this. All right, I'm gonna run this. And then, so 256 times this software is making a guess at the first byte of the key, separating those two traces into two groups, subtracting them together, and telling me which guess had the highest peak. In this case, it starts off 2B70, right? Those are the first 2 bytes of the key. This is only operating on information from those power traces, right? This is not interacting at all with the microcontroller. There's nothing up my sleeve, okay? And you can already kind of see this going in about, I don't know, 2-3 minutes, right? Just by looking at the power traces, I'm going to be able to recover the private key inside this STM32. Okay. I'll show you the shift booster now. There was my demonstration. I had a video just in case. Coup time. All right, so even if, nope. All right. So hopefully all of us are still playing, even though we're not necessarily tallying all of our scores. Question 3, what side channel does DPA rely on? Yeah, power consumption, because I'm watching those power traces, right? The power traces reveal information to me about what's going on inside my microcontroller as it's doing the encryption. All right, number 4, true or false? Side channel attacks exploit information leakage from a device rather than breaking the cryptographic algorithm itself. Yeah, too easy, yeah. We're not, I mean, AES is cryptographically secure. You're not gonna brute force that thing, but the device itself gives us enough information to recover that key. True or false? DPA typically requires a single power trace to reveal secret information. Yeah, false. I can definitely get information about what a microcontroller is, or a processor is doing with a single power trace, but not enough to do my differential power analysis attack, right? I've got to average a whole bunch of traces together to kind of cancel out some of that noise to see the contribution in that power trace from a single bit in that microcontroller. All right, an attacker measures how long a password comparison takes and infers characters one by one. This is an example of yeah, very good. Timing attack. That was one of the first side channels we looked at. Okay, cool. Let's go back here. All right, cool. So there's a whole bunch more cool stuff we can do with side channel attacks, but I'm going to move on now to level 5, fault injection attacks. And to me, this is further on the spectrum because I'm starting to actually interact with my device. Some of the faults are strong enough that I can actually break them. So a little bit more intrusive. All right. So all devices have valid operating ranges, outside of which the manufacturers kind of just say, hey, all bets are off in terms of what this thing is doing. All right. I've got a standard little D flip-flop here on the left, and whichever manufacturer is going to make that device, they're going to have requirements in terms of what range VCC needs to be in order for this thing to do the D flop thing. There's a certain setup and hold time and certain logic values on the data in that have to be met in order for this thing to do D flip-flops. On the right, I've got excerpts from a data sheet for an STM32 microcontroller. Kind of, same story. We're seeing a minimum operating voltage range of 2.0, so anything less than that, ST just says, hey, don't expect this thing to work. I've got minimum and maximum clock values that I can send into my microcontroller to get a valid clock for it to run. And in each of these cases, like we said, the manufacturer just says, all bets are off if we don't meet these criteria, right? And of course, if we try to run this microcontroller from, 1/10 of a volt, it's just not going to work. But the question stands, well, what if we're just a little bit outside that operating range, right? Or what if we glitch the power down to ground, but for a microsecond right around the clock edge? Or what if we sort of double pulse the clock real quick? For one clock cycle, this thing looks like it's at 96 megahertz when the maximum should be 24, but then it keeps running correctly. What happens then? Okay, well, now we're in a weird range where the manufacturer just says, hey, we just can't guarantee what it's going to do. In effect, we don't know. In a lot of cases, we just sort of cause the device to reset. We break it in some way. But occasionally, these little glitches will cause the device to continue running, albeit with having a skipped instruction or a corrupted instruction. Or we can potentially cause the device to sort of flip a bit in one of the registers. It's not necessarily deterministic, but it doesn't necessarily have to be for this to work. All right. Here's an example of us being able to use this sort of ability to fault a device intentionally to get around a password check. Okay, so I've got some sample code here. The key requirement, I'm gonna try to get it out of the way, is that I'm checking the user's password. So this is like going back to that first example where we're doing a string compare. And in this case, I'm going to set the default to allow login. Password OK is default set to 1. Then I iterate over my password. If any of them don't match, then I say, oop, no, not allowed. Right? We're not going to let this individual into the device. All right. To do fault injection attacks really well, a lot of times we have to look at the assembly because we are targeting specific instructions that the microcontroller or the processor is doing. So it turns out this little setting of the flag variable to this value of, hey, don't let the user in, amounts to one store instruction in the ARM assembly. All right? One store instruction. If I can get the microcontroller to sort of skip that instruction or garble it in some way that it just doesn't execute it, then the default value allowing me access to the device stands. So that's what I'm going to do. There's hardware on the Chip Whisperer Nano that lets me do this. It's called a crowbar. Basically, it's just a MOSFET between power and ground. So I'm just going to slam VCC to ground for some real short amount of time to see if I can get the microcontroller to kind of skip over that instruction. On the Chip Whisperer Nano, for this type of attack, there's really two parameters I can change. I can change how long I wait after some triggering event to perform the glitch, and I can change how long that glitch happens to try to make something, useful. And so at this point, I don't know what those two values need to be. Hardly ever do you actually. So fault injection attacks are sometimes difficult to get to succeed because there's just a lot of throwing darts at the wall and seeing what sticks, right? But that's what I'm going to do. Right? I'm going to sweep these parameters while I'm continuously sending bad passwords to the device to see if I can glitch that instruction. Okay, and I think, yeah, okay. So let me see if I can set this up for us and show you in real time. All right, so again, I'm using the Jupyter notebooks provided by New AE Tech. What I'm going to show you here is over and over again, I'm going to send zeros to my device, 5 zeros in a row. And what this device is, nope, not that, is looking for is a password that matches touch. TOUCH is my password. But I'm just going to send this thing bad passwords over and over again. All right. In my code here, I am iterating over my offset range from 1 to 50. I've had some success in that range finding a glitch that works. I'm going to set how long that glitch is between 10 and 12, and these are parameters that are defined for the Chip Whisperer Nano. And I'm just going to run it and see what happens. All right, so you can see this graph here will show successes and failures. You can see right now I'm not really affecting the device. This count of normal operation, i.e. I send a bad password and the device tells me access denied, is just going up because my glitch is not yet affecting the chip. All right. Eventually, and sometimes it takes a little bit, we'll probably see the reset count start to go up because that means my glitch is long enough to actually cause the device to go into reset. So it's almost a little too long at that point. Oh, no, there it goes. Holy shit. Okay, pardon me. That's okay, I want to support cancer research. Yeah, I got a success, holy cow. Okay, so on the graph, that's that little green X. You can see it down here when my device returned the value 1 in the firmware. Where'd it go? The device returned a value 1. It was returning the value of password OK. So I just had to iterate sometimes, and in this case, it really didn't take that long, maybe 30 seconds or a minute, for me to sort of find a glitch that caused this microcontroller to corrupt or edit that instruction and gave me access to the device. Nope. All right. So like I said, a fault doesn't necessarily have to make sense for it to work. It just needs to be repeatable. There are a number of ways to induce faults, right? We talked about two so far. I can sort of glitch the power supply, and there's even a couple of different ways to do that I haven't shown. I can glitch the clock. We'll look at lasers a little later. But another neat one is electromagnetic fault injection. So I can hover a strong electromagnet on top of my microcontroller and make it create and collapse a really strong magnetic field as the device is operating to try to glitch it. The cool part about that is that now I've got like an XY positioning. So I can actually like target specific parts of my processor. I can like hover over the ALU or hover over the instruction register to like try to target specific parts of my chip. Again, devices in production very susceptible to this. So NXP makes a family of microcontrollers called the LPC. A lot of them have a specific register called code read protection. So if you set that register to a specific value, I can tell the LPC, hey, on boot up, you know, disable certain features or enable certain features to allow or disallow users to read out code from memory or disable the JTAG or something. Critically, if the device or the value in that register is anything other than one of these 4 key values, the microcontroller interprets that as a no protection, all right? So Chris Gerlinski in 2017 discovered that this code of checking that value in that register essentially amounts to a single load instruction, right? I'm going to load the value from the CRP, location to memory into one of my internal registers, and based on that value, I'm gonna allow or disallow certain features in my device, and we can glitch that, right? He successfully demonstrates in this video conducting a little glitch on that value being loaded, causing a device that should be protected by code read protection built into that thing by NXP to not be protected at all. It's actually how the Xbox 360 was hacked in 2011. All right, so the Xbox 360, like a lot of really complex stuff, hardware, starts with some sort of BIOS, right? Goes into a first stage bootloader, second stage bootloader before it loads the actual OS kernel that's gonna run. And along the way, it's conducting checks to make sure that, hey, we've got valid stuff here. Well, turned out checking the hash on the kernel amounts to a single mem compare. Right, so attackers in 2011, discovered that, all right, well, we can load our own kernel into that flash. And all I need to do at the right time is pulse the reset line just long enough to cause the memcompare function to return a 0, even though it shouldn't. That 0 value coming out of memcompare will trick the processor into thinking, hey, we've got a valid kernel here, and boot my code. And this thing can happen fast and sufficiently enough that you could buy mod chips that just sort of slap onto your PCB and in a couple of minutes successfully trigger a glitch that allowed your Xbox to run your own kernel. All right, so take a second. Holy cow, how would you fix the Xbox code? Take a second with the people next to you and see if you can brainstorm some solutions. All right. Oh yeah, I got some Kahoot. All right. True, false. Injecting a fault during the execution of a password check can cause the device to skip the comparison entirely. Yeah, totally. Among other things, right? We don't know what's going to happen, but skipping it could be one of them. All right. Which of the following best describes why a voltage glitch may cause a CPU to skip an instruction? I know, I gotta find a good spot. Yeah, okay, we were corrupting that fetch or decode. We're doing something to cause this instruction to kind of be malformed. Okay, excellent. Okay, level 6. Yeah, this is the mega boss, folks. Okay, with a lot of time and patience and potentially some very expensive machinery and a good bit of know-how, I can scrape off the plastic on top of an integrated circuit, right? Usually I need very strong chemicals. I can do it with strong lasers though, or milling machines. Some folks will just sort of cut devices in half, but as an attacker, I really want this thing to continue operating so that I can do an attack on it. Once the silicone is exposed though, I've got lots of cool stuff I can do, all right? Now that I can see the actual silicon in the transistors, I can conduct optical side channel attacks, right? These transistors occasionally will emit photons as they're switching on and off, which means I can measure that to conduct a side channel attack on this device. I can use strong lasers to induce faults since I can actually look at the transistors in a very similar way that I might just normally use a phototransistor, right, to turn a gate on or off with some amount of light. It gets even scarier, okay? I can use focused ion beams to physically change the silicone on that chip. I can cut traces, I can deposit material, I can effectively cause this thing, you know, with a few limitations to do whatever I want it to, all right? Again, keep in mind that this requires very expensive machinery, really a lot of expertise, but it's there. Okay, a couple of quick countermeasures. So, hope is not all lost, okay? Like you can expect, the world's still working. There are countermeasures to each of these things. And so it involves sort of subverting the attacker's understanding of how the device is operating, okay? So to prevent side channel attacks, what I can try to do is sort of decorrelate the time that my device is doing to execute things to sort of shake off that timing attack, right? I can insert a random delay, right? If I'm randomly delaying after some trigger, then it's gonna be hard for the attacker to sort of figure out what's going on with this string compare. I can rewrite a variation of mem compare that always runs the same amount every time and then will tell me if the answer is same or different. For fault injections, one of the best things I can do is not use default constants, right? 0 and 1 are easily glitched too. So if I use random stuff for my true or false, or if I can XOR in these characters here to do my mem compare, then at the output, if one of those things doesn't match, I've got an indicator that someone glitched an instruction somewhere. There's some really advanced stuff I can do if I want to verify the control flow, right? I want to verify that my software actually executed a certain branch, but simple things I can do are just check that, hey, my loop counter should have gone to 1,000 before I exited the loop. If it's not, maybe one of those iterations was glitched or something. So to me, key point, right, is that step one was knowing that these attacks exist, right? Knowing that if we're developing a device, we need to think about that hardware security. In many cases, the threats are not big, the attacks they can do are not crazy, and I don't need exorbitant countermeasures, but occasionally I might, and the best thing I can do is just be intentional about that. Okay, I think I'm running out of time, so we're gonna skip this. Do I have any time for questions? Okay, I'll tell you what, I will take questions up at the front here. I think the best way for me to hand out these super cool prizes is if they are all of interest to you, think it'd be cool to own a Chip Whisperer Nano or own a copy of this book, come up, all right, I'll find a fair way to hopefully divvy them out. You can ask me any questions up there. Otherwise, thank you so much to all of you for being here and to the presenters, the organizers at Jawncon. This has been a blast. I hope you enjoy the rest of the conference.